do you build creature comforts into a tower of steel and glass? From freight hoists to high-speed pressurized elevators. From ice to nice. In Los Angeles, we're constructing a mega building from the ground up. And we'll use it to explore the development of the systems that make the high life comfortable while meeting the people who design them. Now, building a skyscraper, the human environment on Modern Marvels. For the past year, 8 months, and 20 days, the builders of the new California Department of Transportation headquarters in downtown Los Angeles have been busy pouring concrete, erecting steel, and installing walls and windows. The massive 750,000 square foot office building looks almost completed from the outside. But the structure is still pretty naked on the inside. It'll take another 7 months to finish installing the heating, ventilation, and air conditioning system, and elevators. These are the things that make working in a large office building possible, even bearable. Beyond the introduction of steel cage construction, no invention helped buildings, including our own, climb higher than the elevator.
If we did not have passenger elevators, we don't have the modern multi-story office building because people won't walk more than 2 or 3 floors off the street to easily reach an office.
The Caltrans building will have 19 elevators to shuttle its 2,000 employees to upper floors. Kone Incorporated will soon begin installing them. But in the meantime, Clark Construction is running a temporary man lift to move workers and materials. At the helm, Bobby Jeffers, man lift operator extraordinaire.
Yeah, you see, you guys, this is a man lift operator's life. You're always getting loaded and you're always having your ups and downs. I've been running the man lift for 25 years all over Southern California. I've built hundreds of buildings. I'm the main person that brings everybody up. The job won't run without me. Whoa!
The site uses an operator for a more efficient flow of materials.
Okay. If I take you down, can I get a nice smile out of you guys?
Going down.
Okay, ready? Okay, hang on. Hang on, baby.
Bobby decides which subcontractor is performing a more crucial function at the time.
We all have to wait our turn.
That's right. You guys going up or down?
Bobby prioritizes the pickups, but no one cares because he's also assumed the role of site stand-up comedian.
Yeah, I haven't eaten in 3 days. I've been on a diet. A liquid diet, beer and wine. Where are you going,
Bobby's man lift will only operate until the first 2 permanent elevators are running. Like most of the elevators used in high-rises, these are what's known as roped traction elevators.
This is the elevator car. Cables are attached to the car, go up to the top of the shaft, and then over a pulley or shiv, and then back down the shaft to a set of counterweights that balance the car. Attached to the shiv is an electric motor, and when it operates, it turns the shiv or pulley, and then the car goes up or down the shaft.
Okay, we are in the pit. This is the bottom of the elevator.
At the Caltrans site, Ron Caborn with Kone Incorporated is responsible for getting all 19 elevators up and running. The first step in the installation process is to attach the guide rails to the sides of the shaft.
Our main part of the elevator is our guide rails. This is what the elevator travels on. It's very important that the guide rails are plumb. Anything crooked in the rail, the faster the car travels, the more you'll feel it. These cars travel 500 foot a minute. It's not a real fast car. It's not real slow. It's kind of in the middle.
Electric traction elevators are the most prevalent.
Okay, we are in elevator 17 machine room. This is on top of the hoistway. This is our hoist motor, which we have the driver under here with the hoist ropes on it. As it spins, it picks the car up and down, counterweight up and down.
The counterweight on this elevator weighs about 12,000 pounds. That's the weight of the car, plus 50% of the car filled to capacity. This helps ease the amount of work required by the hoist motor.
Okay, right now we're roping up our cars using this elevator steel cable. We're starting out with the spools up at the very top, letting in one dead end all the way down, feeding it through our counterweight sheave. Then we're attaching it with a rope, and then they'll pull it all the way back up to the very top where they put a shackle on it and hitch it up to the hitch plate.
The Caltrans job is going pretty smoothly. Then, one of the elevators hits a bump. After successfully roping 8 elevators, the ropes from one have unexpectedly jumped off their sheave. Dangling over an open shaft, the engineers try to sort out the tangled ropes and get them back on the sheave.
Okay, this is 1.
Yes.
This is 2.
Yes.
Okay. Okay, establish the next one.
Wait. This one I'm shaking. Look where I'm shaking. This one is 1. This one is...
Okay, let me spell it out to you. Grab the number 1 right here, put number 2 right here, so I can get 1 and 2 in order here, because I can't see it.
The engineers worked 2 days to sort out the problem.
It was quite a project to fix it. We did have it all back up and running again. We noticed that the ropes were damaged. So actually, we have started replacing them. We have to put all new ropes in the car.
Besides the hoist motor, the elevator computer, or controller, is also located in the machine room, above the shaft.
This here is our controller. This is the brains of the elevator. It tells it what to do. It monitors what it is doing.
The computer tells the car what floor to go to, when to open the door, and on some elevators how much weight just stepped onto the elevator. And believe it or not, the door close button is actually connected to the computer. The controller also regulates the speed of the car. One of the biggest fears people have about riding in an elevator is a sudden uncontrolled free fall.
It's simply the misconception or misperception we have of elevators from television programs and movies where the cables are constantly breaking and the car plummets sort of helplessly down to the shaft. That is almost impossible given modern safety devices.
One of those devices is the governor, which monitors the speed of the car.
If the car were to fall and go faster than it's supposed to, it will recognize that and stop the sheave from spinning, and it will stop this cable from spinning.
There are also safety brakes under the elevator car, which clamp down on the rails to stop the car in the event of a fall. If all else fails, there's even a cushion in the bottom of the pit.
So we have a hydraulic buffer here. If the elevator were to fall down the hoistway for a short distance, this hydraulic oil buffer will catch the car. This thing compresses. The faster the car comes, the faster it will stop the car.
With all the safety mechanisms, there's really no need to worry about an elevator plummeting down a shaft. But that hasn't always been the case. Elevators used to be slow and sometimes dangerous, yet luxurious. Still, this economically uplifting invention would change the rules of real estate.
Oh. Don't take you 8 hours to do a day's work, does it?
Some people are professional man-lift writers. I mean, you have those on every job, you know. But you can tell the lazy ones can't walk down one floor.
Okay, here we go. Down one? When I was your I used to climb the ladder barefooted, and the ladder was laced with barbed wire so I wouldn't slip.
After 25 years of ups and downs as a man lift operator, Bobby's retiring in 7 weeks.
I think Bobby's great for morale because you come in all tired and grumpy, and he'll make sure that you smile, say hello to everyone.
Did you say good morning to everybody, Juanito?
Good morning, everybody. Come in a bad mood, Bobby's right here, picks you up.
Look happy now, smile. Let's go get him.
Although it might seem like Bobby's been running the man lift since the elevator was invented, mechanized freight hoists actually date back to the late 1700s. English textile mills were among the first businesses to climb aboard. Steam engines or water wheels provided the lifting power to move goods and products. The benefits of elevators were clear, but several deaths caused by freight hoist accidents proved elevators weren't yet safe for transporting passengers. Enter American inventor Elisha Graves Otis. In 1852, Otis installed the first hoist with a safety brake in a factory. The following year, Otis demonstrated his new invention to the public at the Crystal Palace Exposition in New York.
He would have the platform lifted up, and Otis would be standing on it, and then someone would cut the hoisting cable, and the car would fall, and then his improved brake would catch and stop the elevator car, and he would be safe.
Spectators were astonished. The Otis safety brake consisted of 2 wrought iron catches on the car and cast iron teeth on the guide rails. If for some reason the hoist rope broke or slipped, a spring tripped the catches, forcing them into the teeth on the sides of the shaft, stopping the fall. This simple but ingenious device made elevators safer for moving passengers. Soon, the first passenger elevators started appearing in department stores and luxury hotels.
The elevator's introduced as another luxury item, literally as a movable room with upholstered seats, mirrors, chandeliers, and operator. And it was that gracious moving room that carried patrons of the hotel from floor to floor.
But the elevator quickly changed from luxury convenience to economic necessity. The new invention now made taller buildings feasible, altering the economics of real estate forever. Developers soon realized the new elevating device could also elevate office rents.
In 19th century New York, primary mode of transportation is horses. Because of not only the horses but other activities, there's a lot of dirt, there was a lot of noise, smells, and being above that had an obvious advantage.
With an efficient means of getting people to upper stories, the top floors, which previously had been less desirable, were suddenly the most valuable space.
The first commercial office building to employ an elevator is the Equitable Building in New York City, completed in 1870.
The trip from the ground floor to the 9th floor, the top story, took just under 2 minutes.
The business community was highly skeptical because this was a slow and gracious device placed into the fast-paced world of American business. There was a recognition that the elevator had to change if it was going to be successful. And it doesn't take too long before the seats begin to disappear and the elevator starts to move much faster.
Over the next 60 years, not only did elevators become faster, but safer and more reliable. Electric traction motors took the place of steam engines. The first push-button automatic elevators started appearing in the 1920s, making elevator operators obsolete.
There was a surprising amount of skepticism about operatorless elevators. People did not want to run them themselves. They viewed this as too complicated, which sounds very strange to us because they looked the same. Many elevators had buttons very similar to today.
Today's elevators are a far cry from the slow, moving rooms of the past.
Elevatoring is probably the most important thing for a very tall building. If you don't get the people up there, you don't have a building.
Builders of the new Taipei 101 in Taiwan faced greater challenges than normal when designing the ultra-sophisticated elevator systems for the world's tallest building. In a structure this large, just getting people in, out, up, and down presents unique challenges.
这栋楼完成以后，将会有12000人在这里办公。
There will be 12,000 people working in the building after it's completed. We know it's important to transport these people to the floor they intend to go to in a short time. Therefore, we divided the vertical transportation system into 3 zones in order to make transportation go more smoothly. Also, the elevators are double-deck elevators. This doubled the efficiency of vertical transportation.
The Taipei 101 utilizes 61 elevators. The larger double-decker elevators can carry 62 people at a time.
同时我们有最快的
We also have 2 of the world's fastest elevators. The speed of the elevator is 1,010 meters per minute, or 60 kilometers per hour. It only takes 39 seconds to bring people up to the 89th floor.
At 37 miles per hour, the express elevators are the world's fastest. They're also the world's most advanced. The cars are streamlined to cut down on aerodynamic drag and wind noise. Toshiba Elevators of Japan spent more than a year testing various systems.
First of all, we must have a very powerful motor. Secondly, we need a little damper in the cab so that it will not move around too much.
Under each cab is a vibration balancing system, which uses sensors to quickly move weight back and forth to counteract vibrational forces.
And thirdly, we need to pressurize or depressurize the cabin in order to give people a more comfortable feeling on their ears.
Pressure chamber testing helped determine what was comfortable. The 2 express elevators move so fast, they're pressurized on ascent and depressurized on descent. To avoid a sudden change in atmospheric pressure, each cab has a high-pressure blower and exhaust release control system. Engineers on the Taipei 101 have pushed elevator technology into the stratosphere. Back in Los Angeles, the elevator mechanics are making good progress on the Caltrans building's 19 elevators. After 4 months, the first 2 are already up and running. They make Bobby's rig obsolete.
It's last week, Friday, right?
Yeah. Are you gonna miss me?
Oh yeah, everybody's gonna miss you out here, Bobby.
This guy's worked with me since back 20 years ago. And he come in the elevator and said, hey, what?
After 42 years in construction and 25 years as a man lift operator, Bobby's retiring.
Friday will be my last day, January the 16th. 42 years. It's all been good. I've helped put a lot of buildings up. I've brought a lot of cheer and made a lot of guys feel good about themselves. And it's been great. I'm gonna miss everybody. They all been like my second family. I'm inside the elevator, go having my ups and downs at Caltrans headquarters building.
Pick us up on the way forward.
Okay, I'll get you on the rebound again.
Got a man in the shady last week here, huh?
I'm gonna talk to the boss, see if I can get you, after I leave Friday, I'm gonna see if I can get you guys 2 days off.
13.
Hey, we appreciate that.
Saturday and Sunday.
When designing a building, engineers and architects spend a lot of time creating a human environment that is both comfortable and convenient. And that includes creating a safe environment. One way engineers protect the structure of a building is to apply fireproofing to the steel skeleton. On the Caltrans building, fireproofers spray a coat of Monocoat MK6 on the exposed columns. It's a gypsum-based cement-like material that goes on wet and dries to form a hard shell. In the event of a fire, the fireproofing material will help insulate the steel from heat.
A fire in a building can easily reach 2,000 degrees. Structural steel starts to lose its strength around 1,000 degrees, and therefore steel isn't actually any more fireproof than, let's say, wood structure is.
Fires have been the bane of civilization for centuries. Fires spread easily between buildings, which were densely constructed, and most often made of combustible material, such as wood. American cities were no exception.
People were very concerned about fire in the 19th century because they had the experience on more than one occasion of major cities burning down. We don't have that today, but they had the Chicago fire. New York burned twice in the 1830s and again in the 1840s. Boston had a major fire. Baltimore had a major fire.
As early as the late 18th century, architects had begun the quest for what they hoped would be a fireproof building.
That's the first time we see builders trying to construct buildings without using any combustible materials. And that's what fireproof meant. It meant buildings constructed without using any combustible materials.
Unfortunately, the Great Chicago Fire of 1871 showed that merely using non-combustible materials, such as masonry or cast iron and steel, still left buildings vulnerable.
When it was discovered that the structural metal buckled or was damaged by high heat, the idea that it too had to be insulated from the heat led to the introduction of materials to protect structural metal.
Builders started encasing columns in terracotta, fired clay, to protect the structural members from heat during a fire. Later, engineers slathered plaster or concrete over wire to protect structural iron and steel members. When properly designed and implemented, these early fireproofing methods worked well. It wasn't until the 1950s that the first spray-applied fireproofing was introduced. But one of the ingredients of the early spray-on fireproofing posed a hidden danger: asbestos. Asbestos is a mineral which was used extensively in many products because of its fire-resistant qualities.
It turned out that the asbestos versions of spray-on adhered to the steel very well. And asbestos is a known fireproof material, which is why so much of the early fireproofing is laden with asbestos, because it was, in the 1950s, the best material they had, and they didn't yet know about the medical problems with it.
Studies showed long-term exposure to asbestos increased the risks of lung cancer. In 1973, the spraying of asbestos-containing material was banned. And therefore, the fireproofing we're spraying on the Caltrans building doesn't contain any asbestos. Fireproofing is meant to protect the structure during a fire, and as a result, save lives. But occupant safety hasn't always been the primary concern. Over the past 140 years, the emphasis on the protection of property during a fire has shifted to an interest in the preservation of life.
In the 1860s, when some kind of supplementary egress was first required in New York, most inventors came up with these block and tackle things that people were supposed to lower themselves out of their windows, or chutes. So there are just dozens and dozens of patents for totally weird and ridiculous things.
External fire escapes first appeared on tall tenement buildings and factories with heavy concentrations of people inside. But one horrific fire proved how inadequate the flimsy, poorly maintained, and rarely used outside fire escapes were. The most deadly factory fire in New York history occurred at the 10-story Ash Building in Greenwich Village on March 25, 1911. Hundreds of people, mostly immigrant women, were at work at the Triangle Shirtwaist Company, making clothing when a fire broke out.
There were so many combustible things in that building. It was probably like an explosion. It spread very quickly. People could not get out from the stairways.
With the internal staircases blocked, some women tried the one external fire escape, but it collapsed under their weight. The fire department's ladders could only reach to the 6th floor. Although the fire lasted less than 30 minutes, 146 people perished, causing public outrage. Aftermath photos showed the human devastation. But they also showed just how well the building, which used fireproof construction, fared.
The structure of the building was able to withstand the heat of the fire. The terracotta fireproofing worked just fine. One of the reasons that people were so angry afterwards, they said, you know, look at all the effort that's been spent to save the building, but there was relatively little effort spent to save all these people.
The horrific fire sparked changes in health and safety legislation, including factory fire codes and labor laws. Today, a building's life safety systems are as important as any facet of design. Computers can help engineers design ever more efficient life safety systems.
It's called Fire Dynamics Simulator. Actually, it was developed by the U.S. government for modeling these fire scenarios. It lets you build a building and then put a fire in, put systems in like sprinklers or smoke control, and then basically model what will happen during an emergency event and see where the smoke will go, what the temperatures will be like.
The life safety systems on the Caltrans building include 7,500 sprinkler heads, fed by 21 miles of pipe.
It's not like the movies where you see one goes off and sort of everything in the building starts getting flooded. Most sprinkler systems activate based on heat, so that the sprinkler that actually heats up will then fuse and activate, while all the sprinklers that are further away, if they're not heated, won't be pouring water down.
But the sprinkler system isn't the only emergency system. There are also 2 active smoke control systems.
Behind us there's some stairwell pressurization, which is basically a safety in case there's a fire. Pressurizes the stairwell, keeps the stairwell locked tight so there's no smoke can get in it when people are evacuating the building.
Another system inhibits smoke movement between floors. When smoke is detected on one floor, that floor becomes negatively pressurized relative to adjacent floors. In essence, creating a pressure sandwich that isolates the smoke and heat on the fire floor. Life safety engineers hope their systems never have to be used. But by applying the lessons of the past and implementing today's technology, they're helping ensure there is a tomorrow for those stuck in a building during an emergency. One of the most sophisticated systems in any large building is the heating, ventilation, and air conditioning, or HVAC system. Keeping the 750,000 square foot Caltrans office building cool in sunny Southern California is going to be quite a chore, requiring thousands of tons of equipment and 20 miles of ductwork.
Comfort is incredibly important because when people are not comfortable, when they are in an uncomfortable environment, people are less productive.
Arup is the mechanical engineering company on the Caltrans project. They're responsible for designing the systems that keep people comfortable.
Yeah, comfort's a combination of things: temperature, relative humidity, and air quality itself. These are the key components of comfort through the eyes of the mechanical building engineer.
Like every other party involved with the design of the building, mechanical engineers rely on computer software.
It's a computer-aided drafting tool, two-dimensional. What we start with here is a typical building layout. Here is the ductwork, the air conditioning ductwork layer, and on top of that we can start to add the lights, sprinkler heads, those sorts of things.
For complex systems, the mechanical engineer sometimes builds a 3D model to better visualize the way all the components work together. These tools are helping mechanical engineers design even more efficient systems.
We have taken the idea of indoor environmental control from a concept that once was considered the realm of the gods, something that was considered impossible to do, to the point now where it has become so reliable and so quiet, so inexpensive, and so hidden that most people think heating and ventilating and air conditioning is nothing more than a thermostat on a wall.
Before the 20th century, climate control was just a dream. For thousands of years, the only product people had to keep them cool was ice. But ice was primarily a seasonal luxury. However, by the 19th century, American entrepreneurs started harvesting ice in the winter and storing it in insulated ice houses for consumption in the summer. An iceman delivered the cold commodity door to door. But the ice was used in ice boxes for food preservation, not for room cooling. It took the hot lead from an assassin's gun to inspire one of the first attempts at an air conditioning system. In July of 1881, Charles Guiteau shot President James Garfield.
He was shot at the railroad depot in Washington, but lingered on for weeks after that. This was August, and Washington is a notoriously hot and humid place in August. In his doctor's judgment, this was having a negative effect on any chance of him improving, and certainly they wanted to make him as comfortable as possible.
Engineers from the Navy Department decided to adapt a recent invention for keeping food cold. Their device had a cistern filled with water and shaved ice. Ice water trickled down through a perforated metal pipe onto 36 terry cloth-wrapped rollers. A fan at one end blew air over the saturated rollers, then through ducts and into the president's room. At the same time, engineers tried to reduce the humidity by placing a large box filled with ice on the outflow side. Engineers believed the water vapor would condense out of the air because cold air can't hold as much moisture as warm air.
They called it air cooling. But in effect, they were hitting on exactly what it is that makes for modern air conditioning, that is control both humidity and temperature at the same time.
For 11 weeks, the device helped to comfort Garfield, but it wasn't enough to save him. He passed away September 19th, 1881.
The problem is that it required 4 tons of ice a day to operate, just a prohibitive amount, even for the White House.
It wasn't until the turn of the 20th century that air conditioning as we know it was born.
Willis Carrier was asked as an employee of the Buffalo Forge Company to design a system which would control the humidity in the summertime at a printing plant so that the colors would properly register. What he did was to come up with a system which used a combination of cold well water as well as a mechanical refrigeration system to cool the water and then to dehumidify the air. That system that Willis Carrier developed started him on a journey which led to his ultimately being called by many people the father of air conditioning.
In 1904, Carrier applied for a patent for his apparatus for treating air. His device both cooled the air and controlled the humidity. His subsequent work formed the basis for air conditioning that is still used today. Movie theaters were among the first large structures to adopt the new technology. However, the expense discouraged new office buildings from quickly following suit. One of the first high-rises to employ air conditioning was the 38-story Philadelphia Savings Fund Society, or PSFS building.
Howe and Lescaz in Philadelphia in 1932 designed the PSFS building, which is the first modern, fully air-conditioned structure. Air conditioning continues to develop, but it's that moment when the tall building is free to be completely sealed up.
Beyond not having operable windows, the PSFS building had dropped ceilings to conceal ductwork. It had mechanical rooms on several floors to reduce the space required for vertical ducts. Engineers even hid the building's unsightly cooling equipment behind the distinctive PSFS sign on the roof. Even the Empire State Building, constructed just a couple of years before the PSFS building, didn't have air conditioning until 1950. The pioneering techniques first employed by the PSFS building are still being used today. The buildings constructed after World War II presented even greater challenges for climate control engineers. The tremendous use of glass as a popular cladding made keeping interiors cool more difficult. Fortunately, the development of more efficient HVAC systems, tinted glass, and window coatings ensured occupants wouldn't bake inside the glass-encapsulated buildings. At our building in Los Angeles, the first truckload of air conditioning equipment has arrived. The building's about to get a whole lot cooler. At our Caltrans building, the Scott Company is the mechanical contractor responsible for installing the systems the mechanical engineer has designed. To cool the building, Scott Company will install 3 massive carrier chillers, the largest being 30,000 pounds.
This is the mechanical room. This is where, in my opinion, the heart of this building lies. These are chillers which, if you were to think about it, are giant air conditioners. All of the cooling abilities of this building basically come from these 3 units right here. The water is pumped into these chillers, is cooled, forced out to different areas of this building to keep its occupants cool.
This process chills water to 44 degrees. The chilled water is then pumped to air handlers.
This is the air handling unit. Basically what happens is the cooled water from the chillers or the heated water from the boilers comes into these connections. And over here we have a coil. The water runs into this, through this coil, through these loops in this coil, whether it be hot water or cold water. And the air, which comes from this span over here, after it is drawn from a series of filters, comes over this way, goes over this coil, and the air is either heated or cooled and goes through the building to provide either cold air or warm air for comfort. The ductwork routes the air and takes it to where it needs to go.
Steve Hinson is handling the installation of the ductwork.
All the duct, it has numbers. Each one of these pieces got a number on them, and that number correlates with the drawing, exactly where that piece goes.
Scott Company will eventually run 20 miles of ducts.
This is actually the biggest job I've ever run. It's a real big job, and a lot of guys really don't think I should be running a job because of how young I am. I'm only 30. All eyes are on me right now. This job will either make me or it'll break me, and hopefully it makes me.
The 3 massive chillers that will cool the structure will also generate a tremendous amount of heat as a byproduct. So Scott Company is installing 4 cooling towers on the roof to take heat away from the chillers. Water circulates around a chiller to draw heat out of the machine. This condenser water, which is now hot, is pumped via 18-inch pipes to equipment on the roof.
Okay, what I'm working on now is condenser water piping. So, well, one of these 18-inch pipes is about 90 minutes each. They're visually inspected by a state inspector, and they can also be x-rayed if it's deemed necessary.
Basically what we have here is the fan section of the cooling tower, or the top section. The water comes in here on this PVC and it is distributed amongst these nozzles. The nozzles spray the water out in a light pattern.
A fan pulls air up through the saturated baffles, cooling the water. The cooled water is then sent back down to the chillers to be recycled through the system. To provide heating in the building, the Scott Company is installing 3 boilers. The boilers heat water, which is then pumped throughout the building to variable air volume boxes. Each VAV box services 4 or 5 offices. Inside the VAV boxes, coils transfer the heat from the water to the air, which is then forced into the offices via the same ductwork as the air-conditioned air. But creating a comfortable environment is about more than heating and cooling. The V in HVAC stands for ventilation.
Ventilation is a very important aspect of the design of mechanical systems. Ventilation is the process through which you intentionally bring in air from the outside in order to remove or displace the pollutants that exist within a building. Pollutants like carbon dioxide and ozone and formaldehyde and other substances like that.
The air handler units bring in fresh air and mix it with return air from the building. Ductwork then carries the conditioned air into the offices. So we finally outfitted this empty shell with elevators, cooling equipment.
They don't belong here. Just throw the shit out. Look at all that stuff. All right. Just throw it out.
And hot tempers. The complex labyrinth of shafts, pipes, and ducts connecting every sector of the building like a giant web is representative of the diversity of experts it takes to create a safe, convenient, and comfortable human environment. And one of those experts who helped get this building up is retiring today.
Have a good day there. Enjoy your ups and downs with all the guys. Take care of them. Take care of the car. Bye, Bobby. Good luck. See you later.
It's a fundamental belief of ours that great buildings are made out of the unselfish collaboration of all the different parts.
Watching the building go from the ground all the way to the top and meeting a bunch of good people on it, looking back, you know, to be able to tell my family, hey, you see that big tall building? Your dad worked on it. And it's exciting.
From now on, the Caltrans building will have to manage its own ups and downs.